It's working for me.
Great.
All right, cool.
Great.
So I'm Tom Christiansen. This is my first talk at Burning Amp. So I figured I would introduce myself a bit. I have done a bit of education work. I started in engineering college in Copenhagen. I'm originally from Denmark. So that's where I cut my teeth there and continued on at the University of Washington in Seattle. I managed to graduate just as the job market was down after the dot-com bubble. That was fun. So I drifted around the PhD program for a while, and then I landed a job at National Semiconductor. And I landed in their precision amplifiers group, and that really tickled my passion for precision audio because I was working on precision op-amps. I did the LMP 2021. And after the acquisition by TI, I was able to claw on, but ultimately the grinding culture of TI was like, you know, this is too much. I wanted the culture change, so I hopped on a degree in psychology. And you know how you're walking down the street now and you see somebody talking to themselves. You know, 30 years ago, that was a symptom of schizophrenia. Now it's just somebody on the cell phone. Or maybe that's schizophrenia, I don't know. I'm not licensed to judge. So anyway, now I run Neurochrome. I started that as a self-sustaining hobby around 2010, and by 2015 it became my only source of income by choice, and by 2017 it was like, all right, this has potential, and since 2019 to the past 5 years, it's been my full-time gig by choice. And when I'm not stirring up the dust at DIY audio, I enjoy playing ice hockey. I also enjoy photography, so this is a self-portrait that I did a while back. Oh, now we're moving furniture.
Yeah, this is blocking everybody sitting over here.
Oh,
so,
cool, thank
so
you.
no worries. And you're on that side anyway.
And I like standing on the, yeah, anyway. And this is a more recent picture. So anyway, enough about me. Let's talk about audio. So I'm here to talk about op-amp rolling, so the random swapping in and out of various op-amps to see what they do. And one circuit we could do that with is this circuit here. I hope most of you recognize that is a gain stage with a gain of 11. And if we apply a square wave at the input, we expect a square wave or amplified square wave on the output. And if we plug in op-amp A, that is exactly what we get. Well, that's not very exciting. But if we plug in op-amp B, we get this. So now we get massive amounts of overshoot, about 50% of overshoot. And we get some ringing here. So this op-amp B is operating, in my opinion, too close to being unstable. So this is one of those where you push it a little bit, maybe you plug in a longer cable, and all of a sudden your speakers or your tweeter is fried because the thing turned into a power oscillator. Another thing we can do with op-amp A and op-amp B is we can apply a sine wave input. And I apply a 10 kilohertz sine wave that's very low distortion. And I get this harmonic distortion on the output. And it's a little unfortunate that the screen is so low for people here.
Yeah, I tried to.
I think that's what we got.
I tried to raise it.
Okay. So anyway, the distortion is extremely low. It's about minus 128 dB or so. So that's truly excellent. We plug in op-amp B and we get this. So now all of a sudden you have all this grass coming up. And I mean, don't get me wrong, the distortion is still pretty darn good. It's below minus 100 dB or so. So that's not bad, but it's clearly worse than op-amp A. And some of you are saying, well, that's fine. I don't listen to sine waves or square waves for that matter. They sound awful. But how about using a phono stage? So I took my Technics SL3200 that has an Autophone 2M Red, nice Danish brand, cartridge there, and I built a little phono stage, and I plugged the output of the phono stage into my APX 555, and I got this. So now, all of a sudden, op-amp A, which was really my favorite before, is the noisiest of the bunch. Then op-amp B is, it's pretty good, but not the best. And op-amp C, which you haven't seen before, is now my darling here. So if we look at the total integrated noise from 20 hertz to 20 kilohertz, we're looking at 100 microvolts for op-amp A, 42 microvolts for op-amp B, and about 20-some microvolts for op-amp C. Yes, sir?
But why do you care? I mean, you can't hear that, or...
Actually, I would question that, because
okay.
the Phono stage has relatively low gain. I'll show you the schematic in a sec. So I would probably add a bit more gain on that, and then you add 2060B gain of a power amp, and all of a sudden you have hiss in the speakers that's there constantly. So bye-bye black background. Whereas if you used op-amp C, that noise would likely be below the noise of the room itself. So, but that's a very valid point. But what if I told you that op-amp B is about 40 times the cost of op-amp C? Would you rush out and buy op-amp B? Or what if I told you that op-amp A is more expensive than op-amp C? So let's see what what our candidates are here. So op-amp A is the OPA 1612. Op-amp B is the Sparkos SS3602. That is a discrete op-amp. It looks like this. And Sparkos, I happened to bump into the owner of the company at Expo, and he kindly provided me with a sample of these, so thank you for that. And op-amp C is the OPA 1642. And I will openly admit, I have a preference for the TI parts, and especially the Burt Brown, the OPA ones, or the National Semiconductor, the LME ones, or LM. But that's just my preference. But I mean, it's pretty clear that the Sparkos is a lot more expensive, and in some cases it provides better performance, but not all cases. So let's have a look at where it could provide better performance. So it seems like, well, if rolling the op-amps or just randomly swapping out the op-amps can be a little bit like rolling the dice. I mean, because basically, in some cases you get better performance, but not always, and so on. So what I will talk about today is a little bit about what do you get with a discrete op-amp versus an integrated op-amp, what are some of the pitfalls you should look for, and I'll run through a couple of real-world examples, and then we'll have some lesson learned, and no time for questions, because Mark's taking over. No, just kidding. Of course, ask questions during. What's that?
That was my fault, ladies, all the time.
Yeah. I'll just talk faster. So what do you get with a discrete op-amp? Well, one thing you get is a lot of marketing. This is the page 1 of Burson's data sheet. And the Burson data sheet for their very nice looking extruded aluminum discrete op-amp is 2 pages. 1, 2. This is page number 1. And it goes through the painstaking process they went through to design this op-amp and how they matched the parts, blah, blah, blah. I skip all that. And this is the real meat of the data sheet. That is the page 2 of the 2-page data sheet. And this doesn't give me enough information to actually design with this part. Specifically, I'm looking for a curve that's the open loop gain phase curve, because that tells me something about how will this op-amp perform once I have feedback applied to it. The other thing, and I do admit that's probably more related to me than to Burson, but they really hit all of my pet peeves with this data sheet. For example, we have time in Siemens. I'm sorry, Siemens is not the correct unit for time, it is seconds. Somehow 35 volts per microsiemens is greater than 5 volts per microsiemens, because 35 is in the minimum column, I think. And okay, fine. I give up. I'm not going to spend 90 bucks on this part. If you want to spend 90 bucks on this part, have at it. I have actually talked to them, and they have allowed me to purchase the part and then test it, and then I can return it. So I might do that and see how it actually performs. Maybe I can help them out with that gain phase curve. So anyway, it might seem like I'm shredding the discrete op-amps, and I will admit that I'm a bit skeptical of them because they're quite expensive. And with a data sheet like this, then I'm sorry, just don't know what I'm getting. So anyway, let's compare that with a integrated op-amp where we get, marketing, blah, 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 and I'm not knocking the marketing guys. But this is basically, well, this is how the op-amp works. This is some of the key features. We get tons and tons of measured data. We get tons of graphs. I think there's 6 pages like this with a bunch of graphs, including the one that I'm looking for, which is the gain phase curve. And then we get a bunch of verbiage about how this works and the pain they went through to design it and how their managers yelled at them. And no, that's not the dish. That's in reality. And then we get some layout guidelines. So we get a lot of detailed information. So, I mean, don't get me wrong, I don't expect a company like Sparkos to have data sheets this detailed, but I am expecting them to provide me with enough information that I can use the part, and thankfully Sparkos actually does that. Their data sheet is about 7 pages, I think, and includes the gain phase curve and stuff like that, and we'll see that in a minute. So, what we also get with the discrete versus integrated is we get a much higher price for the discrete. These are dual op amps, all of them, and they're about 80 to 90 bucks versus $2 to $7 for the integrated amps. And you can find integrated amps that are more expensive, but this is sort of, I mean, $659, that's kind of expensive for my taste. So anyway, I'm not here just to tell you how to spend your money. I'm just saying that with the discrete op amps, you pay a lot, and the Sparkos is one of the few that I have, under certain conditions, see beat an integrated op amp. That was, 1/50th the price. So, but anyway, let's talk a little bit about stability. It's important that an amplifier remains stable. And that means that it doesn't spontaneously turn itself into a power oscillator. What can happen here, as I hope this is review for most people, but if the phase around this loop here is, if the phase delay is more than 180 degrees, this minus sign effectively turns into a plus sign. And now we have an infinitely building voltage here and an infinitely building voltage here, and now we have an oscillator. And usually not even one with great phase noise, so can't use it for anything. But let's have a look at how this actually works. So now I've just relabeled the various variables in here, and we can see that XO is XI times A, XF is XO times beta, and so on, and we get these 3 equations. And if we combine them and massage them a little bit, then we get this. And I hope that's also a little bit recognized for some people. And that looks a little bit complicated until we realize that if A times beta is significantly greater than 1, then we can basically reduce the equation to that. So now we have the closed loop gain is 1 over the feedback factor. And that's handy because that allows you to make an amplifier that only depends on the feedback factor. And that can be set with a pair of resistors that can be picked precisely and with great tolerance, low drift, etc. So that's what these two are. That is the feedback network. And it's a resistive divider because the op amp has near infinite input impedance. There's no current going here, so basically the voltage at this point can be calculated with this equation here, which is just a simple voltage divider. Now, how do we use that? Well, we grab the gain phase curve, and then we plot the 1 over beta. And I'm using a little bit of a trick here, because what you'll see in textbooks is that, well, that is your loop gain there, and what you really should do is you should draw the loop gain and the loop phase, and from that figure out the phase margin. But if 1 over beta is a straight line, you can actually read that directly off the plot by reading the phase at the crossover point here. And that gives you the phase margin, which in this case is about 75 degrees. Are we good? And it just turns out that for a second order system, you can derive some, or somebody can derive some equations that describes the maximum overshoot as function of the phase margin. You've probably heard that you want a phase margin of at least 45 degrees, and that's just to make sure that the amplifier remains stable. What 45 degrees of phase margin will give you is actually a lot of overshoot. So let's look at what the overshoot is at 75 degrees. The way we use this curve is to grab the 75 degree point here. We go up to where it intersects with the phase margin curve. That gives us a damping ratio of pretty darn close to 1. And we can drop down to the x-axis and we see that we have hardly any overshoot. I admit this curve is a bit complicated to use. It's basically 2 equations on the same plot, and the equations are not nice. But that's how you use it. And that's also what we get in reality, right? So with the OPA 1612, there is hardly any overshoot. In fact, that little, it does look like there's a little curvature there, but that could just as well be the oscilloscope probe that's not perfectly calibrated. Whereas if we use the Sparkos, and so thank you for putting the curves in the datasheet, Sparkos, that was great. Now we can figure out the phase margin, and in this case it's about 38 degrees. So what I said before is that this curve is valid for a second order system, and this is not a second order system. I mean, this slope is minus 40 dB per decade, and then you have a pole zero pair out here, and they actually use a pretty fancy compensation. So technically this curve is not exactly valid, but for a phase margin of 38 degrees, we should expect about 30-some% overshoot. What we get in reality is about 50% overshoot. And that's because the equations break down a little bit because the Sparkos is more complicated than the simple second order system. And I just put a picture of this is the amp itself with the BNC connectors on input and output. So the question becomes, well, what can we do about this? Well, we can add a capacitor across that 10 kilo ohm resistor. And you have probably seen that trick applied more than once. And maybe, hopefully, scratched your head, going, oh, I wonder how that works. And this is how it works. So it takes your 1 over beta from a straight line to this shape here. And now my simple hack of just reading the loop phase off of the plot doesn't work. What we can do, I mean, really if I was performing a proper stability analysis, I would look at the loop gain, and we can see that the slope of the loop gain will change here because 1 over beta and the open loop gain, they approach at a different angle. So anyway, I would work out the phase margin for that. What we can see...
Tom, what'd you do?
Burning amp is over. Everybody leave.
Bye-bye. Well, at least gravity still works. Somebody's got to test it periodically. What we can see here, we can use what's called the rate of closure. So basically we see maybe we'll look at that later. What we can see is that the two curves approach each other at about 20 dB per decade. So the amp will be stable under this condition. I was just a little too lazy to actually calculate the phase margin. But it is stable, and it gives a little bit of a blip of overshoot, but this is actually pretty nice. The drawback is that now we have more capacitance to charge, so the slew rate here is lower. Trade-offs, trade-offs. And let's look at, so now that we have a stable amplifier, we can apply a sine wave to it. And this is what the distortion looks like. So this is THD plus N versus output voltage for the 3 op amps under test here. And we can see that the OPA 1642 is the top line here, so that performs a little bit worse than the rest. We can also see that the Sparkos and the OPA 1612 are not quite line on line, but pretty close. And the Sparkos clips a bit earlier than the rest. It's basically not full rails rail on the output. And that's fine. It still provides over 8 volts of output voltage, so that's plenty. If we load it a bit heavier, so this time with a 600 ohm load impedance, we can see that the OPA 1642 now starts being a bit noisier, and we can also see that it starts distorting quite a bit earlier, and also that it starts clipping at about 8 volts. And that's a bit surprising, but the OPA 1642 is not designed for high output current, whereas the 1612 is. So the 1612 performs a lot better, but actually, quite interestingly, until the point of clipping, the Sparkos now overperforms or outperforms the 1612. So that's an interesting observation. We can also look at distortion versus frequency. So the eagle-eyed observers out here might notice that it looks like the THD at lower frequencies is higher in this plot than it was in the previous plot, and that's true, and that's because I changed the measurement bandwidth to 80 kilohertz from 20 kilohertz. So that's just the extra noise from 20K up to 80K that you see there. Then you also see the OPA 1642 starts creeping up at higher frequencies, and at higher frequencies still, the Sparco starts distorting a bit more. And I believe that's just the loop gain of the Sparcos that's rolling off at this point. Whereas the OPA 1612 is basically flat with frequency, except for a little bit of a rise near the end. That is seriously impressive performance, and I think that's due to the combination of feed forward and feedback within the OPA 1612. That's pretty neat. It's pretty amazing what $6.50 will buy you versus $80 for the Sparcos. But anyway, so gain stages are fun, they're simple, easy to analyze. Let's look at something that's a bit more real. And in this case, it's a phono stage. It's not my design. I grabbed it from Douglas Self's small signal audiobook. And I did simplify this to one resistor, but aside from that, I built it as is. And this is what it looks like. I also went and added AC coupling on the input just so I wouldn't fry my cartridge in case the op amp misbehaved. So that's what it looks like, and that's what it looks like on the bottom, so not exactly fancy, but I'm not going to win a design award with this, but it actually performs pretty well. And here's the performance. So according to Doug Self, the gain at 1 kilohertz should be 1, and it should be 30 dB, and it's smack on 30 dB. It's a bit hard to tell from this curve whether it meets the RIA target or not, but I can apply equalization on the AP, and then I can measure the RIA target. Basically, the signal goes through an inverse RIA, then through my phono stage, and then it's measured at the output of the phono stage, and that's brilliant. So we can see it's within the RIA target, or it meets the RIA target within plus minus 0.6 dB, or 0.06 dB, sorry. So basically, it's spot on. And that's just with 1% metal film resistors and plus minus 5% ceramic caps. So that's pretty good. This is a circuit burrito. I don't think I'll work at Chipotle anytime soon with these burrito making skills, but hey, I like to do this when I measure high gain circuits, and especially circuits that are a bit susceptible to noise from the outside world. I wrap the circuit in anti-static bubble wrap and then wrap it in tin foil. So the foil is grounded here with an alligator clip that goes to the analyzer ground. These two BNC cables hook to the analyzer, and then we have power supply coming in, and this goes to my Techniques SL3200 with that Orifone cartridge. And then we look at the noise at the output of the phono stage. So this should look familiar, we just saw that earlier, except I put the numbers on there. And it's interesting to note that the OPA 1612 is touted as this ultra low noise op amp, and it's super fantastic. I think it's like 0.9 nanovolts per root hertz, if I remember correctly. I don't remember exactly, but it's very low noise anyway, very low voltage noise. The Sparkos comes in somewhere in between. That's really not bad. And then but it is bettered by the OPA 1642. And that's interesting because the OPA 1642 actually has about 5 times the voltage noise of the OPA 1612. So maybe the answer is not in the voltage noise. In fact, it is in the current noise. So there's some noise current that comes out of the input of the op amp. And with a moving magnet cartridge, that noise goes into the cartridge. And because the cartridge has a rising impedance with frequency, you actually see a lot of contribution from the noise current. So if you're designing a moving magnet phono stage, pick an op amp with low noise current. And the OPA 1642 is really the performer here. They don't specify the 1/f noise in the table, unfortunately, but 0.8 femtoamp per root hertz, or 800 atto-amps per root hertz. I never thought I used the prefix atto in public. Versus picoamps per root hertz, and I included the NE5534 in part because it's Douglas Self's favorite, and a lot of people also this is their favorite phono stage op amp, and I can see why. I mean, it's an aging op amp, but at 0.4 picoamps per root hertz, that's actually that's a really strong contender. That's pretty low. So the way to one way to roll op amps and to figure out, well, which op amps performs best with in a given circuit is to use a circuit simulation. And the challenge with the circuit simulation is that you need to know the impedance of the cartridge, and Ortofone does not provide these values. I was able to find some values for a Shure cartridge that I plugged in, and there's another cartridge mentioned in Douglas Elf's book. Bob, do you have more cartridges listed in yours?
In the new book.
Yeah,
yes.
in the new book. In
Yeah.
Bob's new book, which is great, by the way, buy it. There is some additional values for those. That's basically the sticking point. The NE5534, there's a good model for that. 1642, 1611, which is the same as the 1612, it's just the single version. And we can look at the output noise spectral density just by clicking a button. And we see that the OPA 1612 has this noise hump in high frequency, and that's its current noise into the impedance of the cartridge, then amplified by the phono stage, gives you that noise hump. But what we're mostly interested in is actually the area under this curve here, and we can have the simulator calculate that. So that looks like this. Unfortunately, Tina TI is not smart enough to run the simulation from 20 hertz to 20 kilohertz. I mean, you can do it, but then the plot gets all funky. But I can use the markers to determine that the noise of the 1611 is about 55 microvolts. So 55 microvolts versus 100 microvolts in reality. So it's a little bit off, but it did at least get the order right between the three op amps. So one way to roll op amps is to do so in the simulator. And you know, there's a pretty good correlation between simulation and reality. So you know, that would save you $80 if you were considering a Sparkus, for example. Or maybe it'll be your justification for spending $80 because, hey, it simulates better than any of the other op amps you tried. So, you know, that's one way of looking at it. So let's, what have I talked about today? So basically, if you're rolling op amps, if you're randomly swapping op amps in and out, be mindful of the stability. You really don't want to create an oscillator. Also keep in mind that just because something is more expensive doesn't mean that it's better. I mean, we saw that even with the OPA 1612 versus a 1642, where the 1642 is the third of the cost of a 1612, but it performs better at the phono stage. And also, importantly, choose an op amp that's appropriate for the application. If you're designing a moving magnet input phono stage, find an op amp with low input current noise. On the other hand, if you're designing a moving coil phono stage, you want an amp with low input voltage noise because the impedance of the moving coil cartridge is a lot lower. And finally, you know, rolling op amps, yep, it changes the circuit performance, I guarantee it, but maybe not for the better. All right, questions, Jim?
If you were rolling an op amp and whatever was originally in there was a bipolar input,
Correct.
have you found that there is any notable difference at line level, not at phone, at line level of changing to a JFET input when it was originally bipolar, or does that not matter?
I doubt it matters much. The JFET might be a little bit lower noise. But it depends on the source impedance. But if we're looking at just regular line level, I doubt there's a huge difference. What you're looking at with bipolar is you have a little bit of base current that flows, and that tends to be higher than the current in the JFET, which is essentially the current through a reverse base diode. So there's a little bit of tunneling current. So the noise are going to be somewhat comparable, but a little bit lower for the JFET. If you're looking at current noise. But for current noise, the better contender is usually the MOSFET input op amp. But with MOSFETs, you get more 1/F noise, so you have more of low frequency contribution to the noise. So that trade-offs run simulation. What else? Yeah, Bob.
Yeah, with the FET versus the bipolar op amp, although it's sometimes non-intuitive to some, you know, a FET op amp usually has higher voltage noise.
Yeah.
The FET op amp, as you pointed out, has almost no current noise.
Yeah.
And I actually, over the years, have preferred using Fed op amps in moving magnet cartridges.
Yeah.
For that reason, they're also much more immune to RFI.
Yeah, because of their
And
higher
a
input
lot of people think
capacitance.
they sound better. So
Okay.
that's a trade-off, that's a judgment call, which
Yeah.
noise you're gonna, put on.
Yeah, it's a bit of pick your poison. I mean, either if you don't trust simulation, then do the math. So, yeah, but that's a good point. I was surprised by some of the FET input op amps where there's basically no input current. And it makes, it makes good sense because you're looking at basically the leakage through silicon dioxide as opposed to leakage through either a reverse-based diode for the JFET or a forward-based diode for the BJT. So yeah. Good.
This is, pardon me, slightly off tangent question, but thank you for your presentation, it was very informative. I'm curious if you've ever used design of experiments, which is an ANOVA-based technique that lets you examine multiple control factors simultaneously and determine the functional response all at once and give you p-values and f-statistics. If not, we can chat later.
Yeah.
I think you might find it really, really valuable for your R&D, which I found very informative.
Yeah.
But as you know, and by the way, I've been to the University at Aarhus, so I know how brilliantly trained Danish scientists are.
That's the other end of the country.
And I trained a lot of scientists in biotech for many years, but my point here is that, as you know, at university, we're kind of taught one factor at a time analysis and experiments.
Yeah.
Design of experiments will let you examine multiple factors simultaneously and tell you which ones will drive the response and how much, and give you a p-value and a z-statistic to back it up.
Okay.
So let's chat later.
Yeah, that sounds good.
Yeah.
But to touch on that though, when I get stuck in a situation where I'm either too lazy to do the math or the math is above my head, what I do is I run a parametric sweep. So with Tina TI, I think you can sweep multiple variables at once. I used to do it in Spectre all the time. It would take forever, but then
The
you
nice
get...
thing is Jump will do all the analysis for you.
Okay,
You
no, that's
just need to
cool.
put in the control
But
factors and the measurements.
I'm just letting everybody know that if you get stuck in that situation where you're really curious about how does variables A, B, and C impact performance, I mean, you know that you're looking at some sort of plane that may or may not have a global minimum in it, but you can usually get pretty close with a parametric sweep, and that's just a matter of setting it up in Tina TI, clicking a button and going away for a cup of coffee.
Yep.
One of your slides, you showed output impedances dropping, and you went down to 600 ohms.
Yeah, the load impedance.
Load impedance, sorry. So could you comment on the discrete op amps versus the integrated op amps in terms of their ability to deliver current? Like the
Sure.
Sparkos did not perform.
Actually, the Sparkos started clipping at 8 volts RMS. And I think that's just because, I mean, with a discrete output stage, you're usually not designing for rail-to-rail because that requires a lot more devices. So even with, are you trying to get it?
No, it's okay.
Okay, so with 600 ohm load, the Sparkos provided 8 volts, and with 100K ohm, provided 8 volt output. So I don't think the output is limited by the current. For the 1642, the output definitely was limited by the current capability of the op amp itself. One thing to note with, so I scratched my head with this for a bit because the Sparkos is rated to provide, I think it's 50 milliamps of output current, but that's the short circuit current. That's not the current that also provides low THD. So does that answer or address your
Kind
question?
of, I was just kind of looking for a comment on discrete op amp versus integrated op amp in terms of their ability to deliver current.
From what I have looked at so far, it looks like the discrete op amps have a beefier output stage. So they would probably be better as a headphone driver, and they would be better in situations that require high output current. That's my best guess. Anyone else? Yep.
You mentioned that for high gain phono stage, you want to look for low current noise. That sort of implies that you would be concerned about voltage noise when you're in lower gain scenarios. Is that true? Or?
For moving magnet, you want to look at low current noise. low voltage noise, it becomes a trade-off between how much noise voltage do you get from the noise current running into the cartridge impedance versus how much noise voltage is there just from the op-amp, the voltage noise itself. And at some point, I mean, if you pick an op-amp that has, I don't know, 20 microvolt per root hertz voltage noise, the voltage noise is probably going to be dominant over the current noise. That's just, I'm making up numbers here, but that's the trade-off you're making. Does that make sense?
Well, that's fantastic. Well, we have to move on. Did you have anything that you want to add?
No, thank you.
Fantastic. Thanks.